Alright, welcome everyone to today's video. We're going to be talking about adiabatic changes. Okay. So, let's kind of review some things that we've talked about, right? So far we've talked about reversible changes, right? Reversible, in our case, typically is implying mechanical equilibrium, right? To imply that external pressure and internal pressure are going to be equal, okay? Right, we've talked about isothermal changes, right, which is constant temperature. Now, adiabatic changes means that no heat is transferred between the system and the surroundings. Okay, so let's consider an adiabatic expansion of an ideal gas. Okay, all right. So our main things here is we're considering an ideal gas, so PV equals nRT, and it's adiabatic, so Q equals 0. Right. Well, we know from our first law of thermodynamics, right, that some change in internal energy that occurs is going to be related with some change in some small amount of heat transfer, small amount of work done. Well, for an adiabatic change, that heat transfer is 0, so it's just dW. Okay. Now, if we recall, we also showed that for internal energy, right, that some small change in internal energy is related with the heat capacity at constant volume times some small change in temperature, right? We talked about this with constant volume calorimetry, right, and showed this to be true, okay, right? And so what that means, right, dW is equal to du, which equals CV dt. So for constant heat capacity, right, the constant volume heat capacity is constant, right? That means that the adiabatic work done is just given by CV delta T, right, which is equal to the change in internal energy, okay? Right? And so that is how we calculate work and internal energy change for an adiabatic process, but the trick comes in often with adiabatic changes about how do we get that change in temperature, okay? Because often for an adiabatic process, we might know the change in volume, change in pressure, but we may not always know what the change in temperature is. And so how do we get the change in temperature given the change in volume? Okay. Before we mathematically show how we get that, right, let's just talk about generally what we would expect, right? So if you're adiabatically expanding a gas, right, so no heat is transferred, but your gas is expanding, meaning it's pushing against some external force and expanding, right? So it's giving up energy during that expansion, okay? So if my gas is expanding and giving up energy, that means its internal energy is decreasing, right? And its internal energy is a measure of its average kinetic energy and things like that, which is related with temperature. So if the internal energy is decreasing, that means the temperature has to decrease, right? So for expanding gas, temperature has to go down. If you compress a gas adiabatically, its temperature must go up, okay? Right? And this is the opposite of what occurs, right, for say, a constant pressure expansion, right, where for a constant pressure expansion, right, an increase in volume corresponds to an increase in temperature, right, and a decrease in volume is a decrease in temperature, right? This is the exact opposite of that. That for an adiabatic expansion, an increase in volume corresponds to a decrease in temperature, okay? And the reason why you can have volume increase and temperature decrease is because it also corresponds to a decrease in pressure, okay? So for an adiabatic expansion, if volume goes up, pressure and temperature drop, and if volume goes down, pressure and temperature increase, okay? All right, so now let's talk about how we calculate that temperature, okay? So let's consider a reversible adiabatic expansion of my gas, okay? So for reversible adiabatic expansion, my external pressure and my internal pressure are equal, and for an ideal gas, that just equals nRT divided by V, okay? Right, recall that the work, the adiabatic work is equal to CV dt, okay? And we can also recall, right, that expansion work, right, how we'd calculate that typically would just be minus P external dV, or minus nRT dV divided by V, okay? Plugging in for that external pressure equaling our internal pressure, right? Now, if I relate these two equations to each other, okay, so I take equation 1 here and equation 2, right, those are both valid expressions for calculating the work. I could use either of those expressions and that would get the same amount of work. Those things equal each other, okay? Equations 1 and 2 equal each other, so if I set them equal to each other, okay, right, I get this equation here. CV dt equals minus nRT dV divided by V, okay? Right, notice t is not constant, I have this dt over here, so I get to divide t onto the other side, okay, right, and I'm also going to move the constants on the other side, so I have dv over v equals minus cv divided by nr times dt over t. Integrating both sides, right, then it just gives us this nice looking equation here of the natural log of our initial volume over the final volume equals cv over nr times the natural log of the final temperature over the initial temperature. So note here that I have initial volume over final volume. That's not a mistake, okay? Remember, there's this minus sign here, and what I did is I took negative ln v final over v initial, and I said that's just the same thing as ln of v initial over v final, okay? So I got rid of the minus sign by taking the reciprocal of my fraction inside my natural log. Okay, so if we define this C here as CV divided by NR, or the molar heat capacity divided by R, okay, plugging that into this equation, right, and then if I pull C up here, okay, then I'll have the natural log of V initial over V final equals the natural log of T final over T initial raised to the C power. So I can just exponentiate both sides, get rid of those natural logs, right, and you're left with this final expression, okay, that relates the volume change and the temperature change. Okay, so if I do an adiabatic expansion reversibly of an ideal gas, then I can calculate that given the change in volume, what the change in temperature is going to be equal to, right? And rewriting this equation, if you want to, right, you can put the T final is equal to T initial times V initial over V final to the 1 over C power, okay? Right, notice that this is a fraction of the initial over the final, right? So if I expand my gas, that fraction is less than 1. So I'm multiplying my initial temperature by a value that's less than 1, right? Which is going to be decreasing that temperature. Okay? All right. And if you want to, you could then calculate the change in temperature by taking final minus initial, right? And then you just get T initial times this ratios of volumes minus 1. Okay. And so then finally, the adiabatic work is that heat capacity, constant volume, times that change in temperature, okay, which is given here, right? Now, I personally don't try to remember all of this, and you don't have to. This relationship here is something that is given. You do not need to memorize that whatsoever, okay? And so often what I would do is I just calculate the final temperature, calculate the initial temperature separately, and then subtract those two numbers, right? You know, and then just plug that into here, right? But you can use this equation and plug everything in at once to find your answer if that's what you prefer. Okay, right? And if we want to look at what the change in pressure is, right, we can use the fact that for an ideal gas, right, the ratio of pressure, volume over temperature initially is the same as that of the final pressure, volume, and temperature. I can rearrange this, okay, and then I can use, right, what that ratio of the temperature is in terms of volume, okay, and I can then set, you know, these two equations equal to each other so that these, right, ratios of pressures and volumes equals the ratio of volume raised to this 1 over C, which again is, remember, C is CV over NR, okay, right? Multiplying the final initial volumes on the other side to combine things, right, gives us that this ratio of pressures is related with the ratio of volumes times 1 plus 1 over C. Okay. And then finally, rearranging things, you can get this equation of the ratio of pressures to the ratio of volumes to some gamma power, where gamma, right, is just this 1 over C, okay, which is the molar heat capacity, constant volume, plus R divided by the molar heat capacity. Okay. Right, you can also, this is just rewriting the exact same equation, okay, and we can note here that the molar heat capacity at constant volume plus R is just the molar heat capacity at constant pressure, so gamma is just Cp over Cv for an ideal gas, right, and so, right, there's this P initial over P final equals V final over V initial to the Cp divided by Cv, right? That's what that simplifies down to, okay? And so that's how I can get my pressures, right, from my changes in volumes, okay? Right. And so finally, just wrapping this up, just briefly talking about, right, adiabatic versus isothermal changes, right? Isothermal is constant temperature, adiabatic is Q equals 0, okay? Right? For isothermal changes, okay, pressure times volume is equal to some constant for an ideal gas. For adiabatic changes, right, it's that pressure times volume to this gamma power, which is 5/3, is equal to a constant, okay? And so, right, if you were to look at the kind of pressure volume curve for an adiabatic versus isothermal expansion, okay, right, this upper curve is the constant T, right, lower curve, Q equals 0, right? So we see here, right, that for the adiabatic expansion, you actually get less work than for the isothermal. Okay, right, because the amount of work done is the area underneath these curves. Okay, right. So adiabatic expansions produce less work than isothermal expansions, right?